Somewhere in California, a small team of engineers types a message to a machine that will not answer for almost 2 days. The command leaves Earth as a beam of radio light, racing outward at the fastest speed the universe allows. It passes the moon before a stopwatch could count 1 full minute. It overtakes the sun's own light within the hour, then slips past Jupiter, past Saturn, past Neptune, into the dark beyond every planet we know. After roughly 22 hours of travel, the message finally arrives. The spacecraft is Voyager 1, the most distant object humanity has ever built, now drifting more than 15 billion miles from home. Then the wait begins again, because the answer has to make the same impossible crossing back. This is not science fiction. This is simply what it costs to talk to something this far away. Voyager 1 launched on September 5, 1977, built for a short mission of only a few years. Fly past Jupiter, fly past Saturn, take some photographs, then quietly retire. Nobody told the spacecraft that plan was supposed to end, with no air to slow it and no nearby gravity strong enough to pull it back. Voyager 1 simply kept going. Year by year, it climbed away from the solar system, until the sun behind it shrank into just another faint dot in the sky. In 2012, after 35 years of flight, it crossed the heliopause, the invisible edge where the sun's influence finally fades into interstellar space. No human-made object had ever crossed that line before. Voyager 1 became our first true messenger to the space between the stars. To understand the danger Voyager 1 faces today, you need to understand how it has stayed alive at all. It carries no solar panels, because out past Jupiter, sunlight is already far too weak to power anything useful. Instead, the spacecraft runs on a radioisotope thermoelectric generator, a sealed core of plutonium-238 that slowly decays and releases heat. That heat is converted into electricity, with no moving parts and nothing to refuel, just the quiet, unstoppable physics of radioactive decay. At launch, this generator produced close to 470 watts of power. But plutonium-238 loses about half of its strength every 88 years, so the output has been falling, slowly and permanently, ever since. By 2026, Voyager 1 is producing roughly half of what it started with, just over 200 watts to run the entire spacecraft, and that number keeps shrinking by a few watts more every single year with no way to stop it. This is the cruel part of the design. The very reliability that makes radioactive decay perfect for deep space also makes it impossible to negotiate with. A broken solar panel might be fixed, a drained battery might be recharged. Decaying plutonium simply keeps decaying, whether anyone is ready or not. So every year, the engineers at NASA's Jet Propulsion Laboratory have to make a brutal decision. Something on board Voyager 1 must be switched off permanently, just to keep the rest of the spacecraft alive. Voyager 1 originally carried 10 scientific instruments, built to study everything from magnetic fields to cosmic rays. One by one, across nearly 5 decades, most of them have already gone dark, starting with its cameras. Back in 1990, in early 2026, a routine maneuver caused an unexpected dip in the spacecraft's power. It was not a disaster, but it was a warning, a sign that the safety margins had grown dangerously thin. To avoid an automatic shutdown sequence they could not easily control from such a distance, the team made the call themselves. They sent a command to permanently power down one of the last working instruments, ending nearly 50 years of continuous data collection in a single afternoon. Only 2 instruments remain active now. One studies the magnetic structure of interstellar space. The other listens to the faint electromagnetic hum of the same. But the team refuses to simply let the spacecraft fade out instrument by instrument. They have a plan, and they have given it a bold, almost playful name: the Big Bang. The idea is to reorganize several of the spacecraft systems at once, in a single coordinated move, instead of slowly losing pieces one at a time. Done correctly, it could free up enough power to keep Voyager 1 meaningfully alive well into the 2030s. But nobody wants to attempt something this risky for the first time on a probe 15 billion miles away. So the engineers are testing the procedure first on Voyager 2, its twin, which sits closer to Earth and has a slightly healthier power supply. If those tests succeed, the same maneuver will be attempted on Voyager 1 later this year. And there is one quiet, hopeful detail. When they shut down that last instrument, they deliberately left a tiny motor inside it still running. If the Big Bang frees up just enough power, there is a real chance they could bring that instrument back to life. One more chance to listen to a region of space that nothing else built by. Humanity may reach again for decades. Power is not the only enemy out here. Interstellar space sits just a few degrees above absolute zero, and the spacecraft's fuel lines will crack if they ever get too cold. So every watt is a trade-off. Every watt spent on staying warm is one less watt available for science, and every watt spent on science is one less watt keeping the spacecraft from freezing solid. Meanwhile, Voyager 1 never slows down, moving outward at more than 10 miles every second. Sometime this year, it will cross a distance with no precedent in the history of exploration, 1 full light day from Earth. At that point, any message it sends will already be a full day old by the time it reaches us. The spacecraft will exist, from our perspective, in a permanent state of yesterday, and still, against every reasonable expectation, it keeps speaking to us. A machine with less computing power than an old desk calculator continues to report on a place no instrument before it had ever measured from the inside. There is no second Voyager waiting to take its place. The next mission capable of reaching interstellar space and sending real data home is, by the most optimistic estimates, decades away. Eventually, a final command will be sent to Voyager 1, though no one can say exactly when. The engineers at JPL are doing everything in their power to push that day as far into the future as possible. When the power finally drops to low, the science will stop, and only a silent carrier signal will remain, carrying no information at all. In time, even that faint signal will fade into the background noise of the universe, and the spacecraft will go quiet for good, but it will not stop moving. In roughly 40,000 years, it will drift within about a light year and a half of a distant star, carrying its golden record of music and greetings from a world that, by then, may not even remember it was sent. That day has not arrived yet. Right now, today, engineers are walking into a control room before sunrise, writing commands for a machine built before most of them were born. Today, Voyager 1 is still out there, still listening, still speaking. And somehow, against every odd the universe could have stacked against it, we are still listening back.